The last topic in this chapter is nonlinear models. You can classify the nonlinear models into three categories. The first category is what appears to be nonlinear, but you can think of it as a linear regression. Say, for example, here, if you have a single variable, x sub 1, as the predictor variable, and if you want a nonlinear function, you can say x sub 1. You can set up the model as y equal to beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 1 squared. So you will have, when you start with, the data will be like you have the y data and you have the x data. Then you simply square each value of x into x squared. So x sub 1 and x sub 1 squared. So you have x sub 1 squared now acts as though it is a variable on its own. Like it is x sub 1 and x sub 2, where x sub 2 is simply x sub 1 squared. Of course, x sub 1 and x sub 2 squared are going to be perfectly correlated, and therefore you're going to have multi-collinearity problem. But at least we are now trying to fit a nonlinear function. We are not worried about multi-collinearity at this point. Or if you have two variables, you can have interaction term as well. So we have x sub 1 squared, x sub 2 squared, and then an interaction term would be x sub 1 times x sub 2. So you have the two columns to start with, x sub 1 and x sub 2, and then you square x sub 1, square x sub 2, and that gives you two more columns. And then you multiply x sub 1 and x sub 2, that will be a third column that are created. So you have the original x sub 1 and x sub 2, and then the other three columns are created by us by squaring and multiplying them together. And then we just simply apply the regular linear regression function. Okay, so that's one category. Another category of nonlinear model is if the model appears something like this: alpha times x sub 1 to the power of beta sub 1, and x sub 2 times x sub 2 to the power of beta sub 2, and then times an error. And you cannot just transform x sub 1 and x sub 2 into other columns in this case, but by taking a logarithm on both sides. Okay, so you get ln of y in that case, okay, and then ln of alpha plus beta sub 1 ln of x sub 1, okay, and then plus beta sub 2 ln of x sub 2 plus ln of error. So that's how the logarithm will work. Now you see that this has a linear structure. So if you replace ln y with y star, ln alpha as alpha star, and so on, then you end up with a model like this. And you see that this appears like a linear regression model. So what you have to do is you take the x sub 1 column and x sub 2 column and make these transformations. So transform y into ln y, transform x sub 1 into ln x sub 1, ln x sub 2, and then fit the model. After fitting the model, you reverse all these logarithms that you have taken, and the reverse of logarithm is exponential, exp, and that will work. So that's the second category, where the model is not linear at all, but you linearize it using some transformations. Then finally, the third category is when you have a function that simply cannot be linearized even with transformations. Okay, something like this. Okay, so alpha times x to the power of delta, then plus beta times z to the power of gamma. So this model simply cannot be transformed into a linear transformation, and therefore we have to use solver to find the estimates for alpha, beta, delta, and gamma. And we already looked at an example of how to use solver in the previous videos, so we'll use a similar approach here. The same is the case with an S-shaped trend. Suppose if you have an S-shaped trend where the product sales takes off and then the marginal increase keeps decreasing, it tapers off and steadies through. So if you have a trend, that S-shaped trend, this is the kind of model that will replicate that S shape, and this simply cannot be linearized by any transformation, so you have to use the solver methodology. So these are the three categories. One, that by its nature you don't have to do any transformation, you simply fit a regression model. Second is you transform the nonlinear model into a linear model through logarithmic transformations. And the third is simply use solver. So we're going to look at these examples, and then we will finally end with a logarithmic transformation model that can be used when you have varying variance. So one of the assumptions to be made in regression analysis is that the variance of the residuals will remain about the same. It's not going to steadily increase or steadily decrease as the different values, as values of x changes, the independent variable. If that is not the case, and that gives you problems with respect to reliability and accuracy of your predictions, then you can do this transformation, okay, by taking natural logarithm. When you take natural logarithm of the original data, then the variance will become really small, and therefore the change in variance is going to be pretty minimal. So the assumption of constant variance will be more than likely valid. So that is the last model that we will look at. So let's go to Excel and look at these examples.